Great. So my paper is about federated edge learning or FEEL. And I would like to take this opportunity to thank all my co-authors for their contribution and insights in this paper. So let me begin with, my slide is not moving. Okay, so let me begin with the core definition of federated edge learning. It is essentially a edge learning framework which allows the mobile devices in the network to join the training of a global model without sharing their raw local data. So the participating edge devices can be your mobile phone, can be your vehicles, can be your drones. So by doing so, this can protect the user privacy, the data privacy. And during the training, you can only exchange the model parameters. So on the figure, you can see this is the typical four-step training cycle for federated edge learning. And compared with the traditional cloud-based learning, the federated edge learning has a few advantages. First and foremost, since it does not need to share the raw data, so it can enhance the data privacy. And second, because we have rich computing resources at the network edge. So by allowing those mobile devices to join the global AI model training, we can leverage those abundant computing resources in the network edge. And also, last but not least, it is more context aware, because the training is done in close to the place where the data is generated. Now, let's see what kind of a role the federated edge learning can play in the future 6G. We all know that the vision of 6G is to be AI native. AI native means two perspectives. One is AI for wireless. This essentially means that we can apply AI or machine learning models to optimize the wireless network design and to enhance the efficiency and also increase their adaptivity. Actually, over the past 10 years, you probably have already seen many research papers apply AI to do the let's say channel estimation, beam prediction, coding, etc. Now, on the other hand, the AI native also means wireless for AI. This is essentially to leverage the capability of 6G to enable efficient and distributed model training and inference at the network edge. And eventually, wireless for AI will promote the mobile AI service. Now, from this perspective, the federated edge learning, you can see it is a key enabler to realize the AI native vision. On one hand, federated edge learning perfectly embodies wireless for AI, because it provides a very nice framework to harness the massive data resource at the network edge. And also, it empowers AI for wireless by utilizing its distributed and parallel processing capabilities to drive full-stack innovation across almost all layers of 6G networks, ranging from the radio access network to core network. Now, but of course, there are many several challenges to deploy federated edge learning. The first one is the communication overhead. From the basic training protocol, you already see that to train a model at the wireless edge, we need many rounds of model parameter exchange. This will surely cause us a huge communication resource. So communication bottleneck is one of the major challenge. The second one is the data heterogeneous. You know, each device may see a non-RID data. So if we train directly on heterogeneous data, we may face several challenges, including model drift problem, and also the convergence can be very slow. And another major challenge is the resource challenge. Each device can have can have its own hardware, its own CPU and memories. So how to train a global or shared model among those different devices with heterogeneous resource is also challenging, and most likely the performance may be limited by the so-called the bottleneck or the straggler issue. So in our paper, we have established a new principle we call the task-oriented principle to address those challenges. Here I'm just briefly motivate you what do we mean by task-oriented. We know in traditional data communication it is purely data-oriented, where the communication network is simply a pipeline, and the primary goal is to recover each single bit reliably. But for federated learning, the goal is not just to recover every single bit. The goal is essentially to maximize the speed and accuracy for the learning task. So from this perspective, if we want to implement federated learning on the wireless network, we have to take the learning task into account and then design the so-called task-oriented design. So in the next slides, I'm going to show you very briefly the two work that my research group has done. The first one is to use the CEO problem for model compression. This is because the local model updates at the edge can be viewed as a noisy observation of the global model that we want to estimate. So this is essentially an indirect multi-terminal source coding problem. So by leveraging the strong correlation among the local model updates, we can significantly reduce the communication cost. Another example is the over-the-air model aggregation. By utilizing the waveform superposition nature, we can allow different devices to transmit their local model updates concurrently on the same resource. We can do so. This is because the server is only interested in the weighted sum of these local model updates. It is not interested in each individual model updates. So therefore, by using the over-the-air model aggregation, the overall communication cost becomes independent of the number of edge devices. So I hope with these two case studies, I have convinced you that why task-oriented communication can help us overcome the communication challenge in federated learning. Now, in return, how would we apply federated edge learning to enhance the 6G network design? So here we also have three use cases that my research group has done recently, and these are all related to the L interface technology. For example, the first one is about the power control, and the second one is the cell-free massive MIMO precoder. These two problems are very well-known, highly complex, non-convex optimization problem in the communication literature. And by using learning technique, you can surely enhance the efficiency. But the major problem is that if each network trains their own model, then the efficiency may be quite limited. Therefore, to enhance the generalization capability of this learning model, we can apply federated edge learning to solve these problems. So in these two work, we have but we cannot apply federated edge learning directly to train these models. Each of them has their own unique challenge. So that's why we need to optimize based on the specific problem, which is what I would call the domain-specific optimization. And more recently, another work we have done is apply federated edge learning for channel state information or CSI feedback. I believe this is one of the typical use case for AI in 6G standardization. And by using federated edge learning, we can enable each user device to have a personalized CSI encoder, and then we have a shared decoder at the base station. So using the federated learning, we can utilize the own local CSI distribution for each user. And then, but for the decoder at the base station, it can accommodate all different channel distributions. So these are all very good examples to apply Federated Edge Learning to solve the AL interface design problem in the 6G network. Now, looking forward, there are still several directions to go. Nowadays, large language model becomes very, very hot in wireless network, and where the Federated Edge Learning can help is also one of the questions. And for example, in my view, in the future, the LLM could apply this three-layer implementation structure. For instance, the up layer, the first one, LZ layer, the auxiliary layer can be deployed at the network side as a foundation model, and then L1 can be deployed at the base station side for technical domain specific model, and L2 can be deployed at the very edge for scenario specific model. So with this three-layer implementation model, then we can apply Federated Edge Learning to jointly update L1, L2 models. And also we can apply Federated Edge Learning to fine-tune the L0 model. So this is one possible solution. Now, moving forward, we can not just do learning on the edge, but also we have to consider how to deploy the AI model among the network edge. And one open key question is, how can we deploy the AI model at the network edge to balance the different computing power, memory capacity, as well as communication cost across all these different devices, but at the same time ensure the inference integrity. And for your interest, recently my group has done the work on wireless distributed MOE. So if you're interested, you can check out the details. So that's all for my part. Thank you.